completed some basics about RF, and we have seen what is an RF radio. um, we have looked at the basic block diagram. Okay, so let's go to the next slide. So that is radio architectures. So let's revisit this block diagram. Now I have showing you a picture which is zoomed in. So you can see that I showed you the baseband block, or the block which operates at lower frequencies, and then you do an up conversion to the requisite band, and then you do some RF processing and you send it over the antenna. So what is RF processing and what is up conversion? So I told you baseband, it could be your voice frequency or audio frequency. If you are taking an example of audio signal, it is below 20 kilohertz. But if I have to transmit it over the air, then you can see that it has to be within this radio spectrum. So very specifically, it has to be within this microwaves. So if you see this section, what is called as microwaves, so you can see that all your mobile phones operate in this range. So we discussed about 4G and 5G. If you remember, we said that it starts from 400 megahertz or 700 megahertz. It can go up to 7 gigahertz in sub 7. Then for millimeter wave, I showed you that it starts from 26 gigahertz. It can go up to 53 gigahertz, right? So basically it falls in all this region. Okay. So then what do we understand? The conclusion is RF processing refers to higher frequency or band pass compared to base band. When you talk about base band, we are talking about these low frequencies here. Okay, you can see here 3 kilohertz, 10 kilohertz. We are talking about these frequencies from a mobile phone perspective. These frequencies are the base band frequencies. And whatever you see here, these are the band pass or the RF frequencies. RF, microwave, we can call any of the term. Okay, so this is band pass, this is base band. Okay, let's go to the next slide. Now let us look at few radio architecture. So if you are doing your masters, or if you have completed your BE Tech, I'm sure you would have heard about super heterodyne architecture. So this is one of the earliest architectures. So you can see here we have this is the radio portion that I showed you. This also includes up conversion and down conversion. That means what is coming on the left side is from the baseband transmitter. So you remember that picture from the previous slide. Okay, so baseband information is coming from here. Then this is the up conversion block, and you have rest of the RF processing. And on the receive, you have an antenna. You have let's say this is the down conversion process and also the RF processing, and this goes to the baseband receiver. Okay, so this is one of the earliest architectures. So I was reading up online, so it has 100 plus years of history. So initially when the communication started, most of the systems were super heterodyne architectures. So what is the meaning of heterodyne? It basically means that mixing. So you can see when we talk about up conversion or down conversion, it is these mixing blocks that we are referring to. Okay. So what is the point of doing the mixing? We have baseband information. I want it to up convert to the RF frequency. So I'll show you with the picture. So if you remember, I told you baseband is at a lower frequency. So see this axis. This is an x-axis with frequency as this is a frequency axis. So this is your baseband information. The whole purpose of this system is to convert this baseband information into RF information. Okay, this is what you can transmit. And in the receive, what happens? You have this RF information. You have to down convert it to baseband. Okay, so what is a super heterodyne architecture? So I have given here an example. So if you look at this example, so let me write here. So this is your baseband information. So you do a first stage conversion to IF. Okay, that is done by this mixing stage. Okay, so you have baseband information coming here. This does this this baseband enters this mixer, and this mixing stage converts this baseband to IF, and this IF information travels here. Then it enters the second mixing stage, which converts IF to RF. Okay, that's what is shown here. So baseband to IF, IF to RF. So one example, if you're talking about, let's say 5G millimeter wave, you can say that I'm taking the baseband information, first converting it to 12 gigahertz, but the final frequency that is allocated to me within the spectrum is 26 gigahertz. So I have to convert baseband to 12 gigahertz and then from 12 gigahertz to 26 gigahertz. Okay, this is what happens in the transmit section. So all this is all transmit. On the receive side, I will receive this RF frequency 26 gigahertz. First I have to convert it to 12 gigahertz. So that operation happens here. So this converts, input is RF, output is IF. Then I have to convert that IF frequency to baseband. So that is this mixer. So input is IF, output is baseband. Once you have the baseband information, it goes to the baseband receiver. Okay, this is what I showed in the previous slide with the 3 blocks. So those 3 blocks are, you have a baseband section, you have up conversion, then you have RF processing, and then it goes to antenna. On the receive, first block is RF processing. So here, this is the direction on the receive, RF processing. Then you have down conversion here. Then it goes to baseband. Okay. So, so this is a high level architecture. So you can see that in a super heterodyne, you have more than one mixer. So it is called as a super heterodyne because we have more than one mixer. Okay, what is more than one mixer? So you can see that this is the first mixer that I showed you. Let me erase all this. Okay, so this is the first mixer stage on the transmit. This is the second mixer stage on the transmit. So similarly on the receive, this is the first mixer stage. This is the second mixer stage. It is called as super heterodyne because you have more than one mixers. Okay, so does it mean that if I have more than one mixer, like in this case 2 mixers, is it possible to have one mixer? Yes, that is also possible. So you can see in the next radio architecture. So some of you may have heard it is called as 0IF architecture. Okay, why is it called 0IF? So see here, if you look at the picture from previous slide, this is the same picture, super heterodyne, but what has changed? Now I'm converting the baseband signal directly from baseband to RF. There is no intermediate frequency. So how do I accomplish that? I remove one of the mixers. So on the transmit side, I have baseband coming here from this side. I'll use only one mixer and directly it goes to RF. What happens on the receive? I have the RF signal directly converting it to baseband. So RF comes from here, goes here, and this is the mixer stage. From here, output is baseband. Okay, so this is an example of 0IF. So this is not a super heterodyne. Okay, you don't have more than one mixer. This has only one mixer. So in most of the recent designs, right, like you can look at, let's say, all the big vendors like Samsung or Qualcomm designs, if you read through carefully, all their architectures are mostly 0IF architectures. Okay, so the advantage is you can always save on the components here. Okay, so you save on the components, and you can save on the power consumption. The size becomes smaller because you're removing from some components. So all those are advantages. These are some of the advantages. Okay. Now compared to the previous one where I called it as super heterodyne, this is called as a homodyne. That means you have a single mixer, and that mixer frequency or the LO frequency. So this is the local oscillator frequency that is required to convert up convert to RF. So this frequency and the RF frequency, they are same. So LO frequency is same as RF frequency. Okay, that's how you get the advantage, right? So see, your carrier is here, RF. It directly goes to DC. Okay, theoretically, okay, it directly goes to DC. So that's how only if your LO is equal to RF, then basically LO minus RF, you actually get 0. Okay, LO minus RF, you get actually 0 hertz. So that's how you do a down conversion or an up, or here it is a down conversion. So you go from DC to RF to DC. Okay, so that's why it is called as a homodyne receiver. Now there is one disadvantage with 0 IF. So that we have to overcome. So what is the disadvantage? You see that when we do the down conversion from RF to DC, your carrier falls directly on the DC. Okay. Now in communication systems, we don't need DC. Why? Because DC does not carry any information. Okay. Does not carry any information. So we have to eliminate DC. It consumes power. It just consumes power, but it does not carry any information. Why? Because DC is like this, right? If you look at DC current or DC voltage, there is no variation. We want information like this, something like this, right? This carries information. A constant voltage like this doesn't carry any information. It just consumes power. So you want to eliminate that. So remove this. So then we go to something called as low IF. So some of you may have heard about this terminology. So low IF, what we do in low IF, we take the same receiver, and instead of shifting from RF to DC, we shift it slightly higher. Okay, so you can think of this as a super heterodyne because you still have an IF here, but you can also think of it as like a ZIF because you are closer to DC but not really at DC. You're slightly away from it. You're trying to move the carrier away from that so that you're not at DC. Okay, but what is the advantage? So super heterodyne, you required 2 mixers. Okay, ZIF, it was landing on the DC, which is not desirable. We don't want this. So we are taking advantage of both. We want 2 mixers, but now that the IF is very close to DC, it's at operating at a lower frequency. So the second mixer can be within a DSP. Okay. So this is the first mixing stage. Okay. So you have, sorry, this is the first mixing stage is inside the DSP. This is the first mixing stage on the transmit. Second mixer is still outside. So this mixer converts from the IF to RF. Okay. On the receive, you have the same thing. You first convert from RF to IF. Then within a DSP, you convert from IF to your baseband. If the DSP actually supports higher frequencies, you don't even have to convert. Okay, so then it won't be a super het also. It will be a single mixer. You can directly operate at this frequency. So the modern day DSPs actually can operate at this frequency. You don't have to down convert it again. Okay, that's the advantage. Okay. So second element digital domain implemented by DSP. Again, this is based on the implementation. If it's required, you can implement, or you can directly operate in the DSP at the IF frequency, which is you can consider as your baseband frequency.
Please click on like and subscribe to our channel and click on the bell icon for regular updates.